So the last cycle of lectures will be devoted to the proof of the, I've called the continuity theorem. I already stated a simple version. I'm going to give the complete statement right now. So let me denote by G of D the space of probability measures on GL, probability measures nu on the space of invertible matrices with compact supports. For example, the simplest type of elements of GD are measures with finite supports. P1 delta A1, etc. Pn delta AN, where P1, Pn are positive numbers such that the sum is equal to 1. And A1, AN are matrices. A1, AN are elements of GLD. So, and in G of D, I'm going to consider the following topology. I will say that nu is close to, or mu, nu1 is close to nu0 if, this is what the topology means, if nu1 is, if first of all nu1 is close to nu0 in the weak star topology, I want to consider a topology that is finer than the, slightly finer than the weak star topology. This is the first condition, and then I also have a second condition, which is that the support of nu1, which is a compact set, is contained in a small neighborhood. Of the support of nu0. Okay? Not only they are close in weak star topology, but I also want that as nu1 gets closer to nu0, the support becomes closer and closer. Now this is the definition of the topology, but of course when I say close or small, this always sounds as a little bit informal. So let me be completely formal by defining the topology through a basis of neighborhoods. Quick way to define the topology is by giving a basis of neighborhoods of any element in GLD, in G of D. And this basis, trying to express 1 and 2, is the following family: V of nu, and then phi1 through phi m, and then epsilon, which is defined as the set of all measures nu prime in G of D, such that So first of all, I'm going to express with any new zero, and this is new 1. First, I'm going to express that the two measures are closed in weak star topology. This means that they have they give integrals to functions that are closed. So the integral of phi I with respect to nu 1 minus the integral of phi I with respect to nu 0 is small, it's less than epsilon. It's for every I. And another second condition, that the support of nu 1 is contained in a small neighborhood of nu 0. Oh, that's easier. Support of nu 1 is contained in the ball of radius epsilon around the support of nu 0. Okay. This is the basis of neighborhoods, and this defines the topology. Once you have a basis of neighborhoods, you can define open sets. An open set is a set is open if given any element in the sets, you can find one of these neighborhoods that is contained in the set. Okay? So this is the kind of topology that I want to consider in this space. And then the theorem says, oh yeah, before that. Now I consider for given nu in G of D, I consider I consider X to be GL of D, M to be the shift space, F is the shift map, okay. Then I consider a function A from M to GLD, which is just given any sequence of the elements of M are the sequences of matrices. So I take the function that associates to each sequence the zeroth term, the zeroth matrix. This is a locally constant. This is a locally constant function. This is a construction that I already presented. I'm just recalling. And then we consider the cocycle, the linear cocycle, F from M times RD to M times RD, given by these objects. XV goes to F of X, AX of V, for that choice of F and that choice of the function A. Okay. Repeat, this is something that I already did, probably at the very beginning, the very first lecture. This is what I called a random product of matrices, the cocycle associated to given by a random product of matrices. And this is a locally constant cocycle because the function is just a projection on the zeroth coordinate, so it's locally constant. Depends only on the zeroth coordinate. Okay, so I'm going to denote by lambda minus and lambda plus the extremal Lyapunov exponents of this random product. And well, they depend on the data, but if you think a little bit, what is the data here? There's not much data really, because this is given, It's just a group of matrices. And then you take the space of sequences of matrices, the shift map on that space, projection to the 0th coordinate. The only choice is this. The only variable in this construction is this. So I'm calling this lambda plus of nu, lambda minus of nu. The theorem that I stated on in the first day corresponded to this choice of nu, and I said those two, the statement that I gave you was that those two numbers, lambda plus and lambda minus, depend continuously on P1, Pn, and on the coefficients of the matrices. So I'm generalizing this by saying that the theorem is the maps, the functions that associate to nu. So these are functions from GD to R. The functions that associate to each nu lambda plus and lambda minus of nu are continuous. Okay. That's the theorem. Okay, yeah, I forgot to say, there's a hypothesis here which is D equals 2. I'm not changing subject, I'm answering your question. First of all, the theorem officially is the theorem for D equals 2. This is written down, and that's something that I did with Carlos Boque. Now, we are working in higher dimensions with Artur Avila and Alex Eskin, and this is probably true. As well. But we are still writing it, so I don't call it a theorem. It's not official, but it's probably true as well. So, I'm still answering your question. The largest Lyapunov exponent and the smallest Lyapunov exponent of random products of matrices, so this is, once I take the measure like this, I didn't say it, the measure mu that is involved here is, the invariant measure is nu to the z. So it's a Bernoulli measure. The largest exponent and the smallest exponent are continuous. Now you're asking about the other ones. In general, so my remark is that the three-dimensional, the general statement, in dimension 2 we don't have more exponents. So the question only makes sense in higher dimensions. If, assuming that this is true, then all exponents vary continuously with the measure. So I'm saying that if we are capable to prove in any dimension that the largest and smallest are continuous, then all of them are continuous. And let me explain why. I explained, I didn't go into details, but I did mention that given a cocycle f, a linear cocycle, we can construct and a number k between 1 and d. We can construct a new cocycle that I call the exterior power. We may consider these exterior powers that are also linear cocycles, but on this space of essentially of linear forms, k-linear forms. And I did some calculations to convince you that the Lyapunov exponents, maybe I should not use the letter k here because k is used for other purposes. The Lyapunov exponents of this cocycle are the sums of Lyapunov exponents of f, are the sums of exponents of L Lyapunov exponents of f. Okay, this is, I didn't prove it in here, but it's proven in there's a discussion in detail in the book. So let me explain exactly what I mean by that. So, more precisely, what you have to do is let lambda 1 hat, lambda 2 hat, etc., lambda d hat be the Lyapunov exponents of f counted with multiplicity. The multiplicity of a Lyapunov exponent is just the dimension of the corresponding Euclidean subspace. Okay, so I'm going to order them in non-increasing order, but of course this is not strict because I may have exponents that are equal and then this is repeated. Okay, so what I'm saying there is that the exponents of the second, the exterior square, the second power of f, are the sums of two elements of this list. So are lambda 1 hat plus lambda 2 hat, lambda 1 hat plus lambda 3 hat, and so on, lambda 1 hat plus lambda d hat, and also lambda 2 hat plus lambda 3 hat, and so on. Etc., all the way up to lambda d minus 1 hat plus lambda d hat. Okay, the quantity of numbers that appear here is choose n 2 by 2, which is precisely the dimension of this space. Okay, and then for the third power, it's the same. You start with lambda 1 plus lambda 2 plus lambda 3. You don't have the right to repeat. You cannot write lambda 1 plus lambda 1 plus lambda 1. Okay, you have to take distinct exponents, except that they may be equal if there is multiplicity. Okay, so this is the largest, and by my theorem applied to f, this depends continuously on the measure, the probability distribution nu. Okay, but Dimitri is interested in the second exponent. Well, this is the largest exponent for lambda 2 of f. So by the theorem applied to this linear cocycle, which is in higher dimension, this also depends continuously on nu. By taking the difference between two continuous functions is a continuous function, you conclude that lambda 2 is also a continuous function of nu. Okay? And then the rest is the rest. So same, you repeat this argument all over. Okay? By the way, it's not easy to put your hands on the intermediate exponents in general. The largest and the smallest are much easier because the largest is given by the sub-additive ergodic theorem. It's just this limit. You see this is the norm of the matrix, and other exponents involve vectors. They are much harder to put your hands on, but this is the way you can put your hands on these numbers, by taking differences. Okay? So what I'm going to do in the next lectures is to prove the two-dimensional theorem, but in fact I'm going to use an argument that is already from this this joint project with Artur and Alex. Okay. So before I get into the proof, let me make an observation. The observation is actually what I've written here. Lambda plus of nu is the limit for mu almost every x in M. Mu is the invariant measure, it's the Bernoulli measure that is invariant under the shift. But we have other formulas. We know that that's part of the statement of the sub-additive ergodic theorem, that this is the limit of 1 over n, sorry, there's a logarithm here, integral of the logarithm of an d mu. And when we proved the sub-additive ergodic theorem, one of the first things that we did was to argue that this limit exists, because this sequence here is a sub-additive sequence of real numbers. And when you have a sub-additive sequence of real numbers, the limit 1 over n of the sequence exists and is equal to the infimum. Okay. I write mu, but mu is a function of nu. Okay, mu is just this product here. Okay. Now. The function for each n, you can think of this as a function of nu. For each nu, you calculate the integral of the logarithm of an with respect to mu. So a is given, it's fixed, it's just this map here, this function. Mu is a function of nu, and so this is a function of nu. I can make it explicit. I write x here and here. What is x? X is an element of M, so it's a sequence of matrices of n. And what do I have here? I have log of this product the first time I iterate, I take the zeroth matrix, alpha 0. Next, I shift and I take the sequence that is now in the zeroth position, which is alpha 1, etc., alpha n minus 1. That's what this means. And then I integrate over all possible choices. So d nu of alpha 0 through d nu of alpha n minus 1. This is just another way of writing this integral here when the data are, when the function is this one and the measure is the Bernoulli measure. Okay? And in this way, I make explicit how this integral depends on u. Okay? Now, my observation is that for each n, this is a continuous function. You may have to spend 2 minutes looking at the formula to convince yourselves that of course, this depends continuously on u in this topology. So it's already continuous if you just use the weak star topology, which is okay. The function that we are integrating here is a continuous function. So it's just using the definition of the weak star topology. So for each n, this function is continuous. And then lambda plus of nu is given by the infimum of these expressions. And there's a general fact, an easy general fact, that if you have a sequence, if you have a family of continuous functions and you take the infimum may not be continuous, but it's certainly semi-continuous. So the function that associates nu to nu, lambda plus of nu, is semi-continuous. Completely general, just because it is the infimum. The tricky part is to decide whether it's lower semi-continuous or upper semi-continuous. And the even trickier part is to remember which one is which. What does it mean to be lower semi-continuous and upper semi-continuous? Okay, the way I remember is that if it's infimum, then it's upper. And upper semi-continuous means that if you have a point and the value of the function at that point, for nearby points, the function may be much lower, but cannot be much higher. Upper means that you cannot go up. Okay? So when you change the point, the value of the function may implode, but cannot explode. Okay? That's the right statement here. So it's something like this. You have a certain nu, you have its exponent. If you take a measure nu prime nearby, it cannot be much higher, but it can be much lower. Okay? So lambda plus is upper semi-continuous. And this is very general. I showed you the kind of detailed the calculation in the case of Bernoulli measure, but it's very general that the largest Lyapunov exponent is this upper semi-continuous function of your data. Okay. Analogously, and there are statements, abstract statements in the book. Analogously, the function that associates to each nu lambda minus of nu is lower semi-continuous. Okay. Now, suppose you have a measure, a probability distribution, which is such that lambda plus and lambda minus are equal. I told you at the very beginning that this is very rare. It's really difficult to have the two exponents being equal. It's a theorem of Furstenberg. But, I mean, it exists. For example, if all my matrices are rotations, then both exponents are 0. So this exists. And what I want to observe is that in this case, we can say something which is kind of nice. So we have nu such that the two exponents, the two extremal exponents are nu 0 are equal. So let us look at some measure nu close by, and let us see what we can say about both exponents for nu. Well, since lambda plus is upper semi-continuous, I can draw a line here, say just epsilon above, and I know that by upper semi-continuity, lambda plus of nu has to be below this line, below the level lambda plus or minus plus epsilon, okay, because of upper semi-continuity of lambda plus. Now, similarly, I can draw a line below, and by lower semi-continuity, I also know that lambda minus of nu lies above this line. Always under the assumption that nu is close to nu 0. Right? The other thing that I know is that lambda plus is bigger or equal than lambda minus. So the big one has to be under this line. The small one has to be below this, above this line. Okay. So lambda plus of nu minus lambda plus of nu 0 and lambda minus of nu minus lambda minus of nu 0, these differences have to be smaller than epsilon if nu is close to nu 0. Both of them have to be in between those two lines, because the big one cannot be above the pink line, and the small one has to be cannot be below the purple line. So both of them are in between those lines, and that means this. Okay? In other words, I've proven the following observation. If you have a point where the two exponents coincide, then that point, nu 0, is a point of continuity for the two exponents. Okay? And that's completely general. This is not frequent, this is very rare, but if you have a point where the two exponents are equal, then automatically, because of this upper and lower semi-continuity, that's necessarily a continuity point for the extremal exponents, and of course for all the other exponents, because they are in between. Okay? So, all this is to say that to prove the continuity theorem, we only have to consider the case when the lambda minus is strictly smaller than lambda plus. Okay, so from now on I'm going to assume this. So let us take nu in GD such that we have this inequality. And now we're going to take a sequence nu k converging to nu in G of D. Okay? What I want to prove is that lambda plus of nu k converges to lambda plus of nu. We already know by upper semi-continuity, we already know that the lim sup lambda plus nu k is less or equal than lambda plus nu. This is another way of writing upper semi-continuity. Lyapunov exponents of nearby measures may be smaller, but cannot be much larger. Okay? Okay, so how are we going to do this? We are going to exploit the connection between Lyapunov exponents and invariant measures and stationary measures that we talked about in the last few lectures. So we know that lambda plus of nu k is the maximum of the integrals of phi d mu k times eta, where eta is the maximum is taken over all stationary measures for nu k. Okay, so let me remind what a stationary measure is. A condition is that eta of the domain D is equal to, you take the preimage of D right, over all the matrices that you have, you average that out with respect to the point x, and you want that the average should be equal to the measure of D This is for every domain, measurable domain, contained in projective space. Okay? This is definition. It's like invariance, except that you have many dynamical systems, and you take the pre-images over all of them, and then you average that out. Well, the way I wrote it, it depends on the measure mu, so I should say eta is stationary for mu k being the the Bernoulli measure associated to nu k. But in fact, since a of x, I already raised it, a of x depends only on the zeroth coordinate. So you can rewrite this just by using the formula for a of x. This is eta of alpha minus 1 of d. Alpha is a matrix, and then you integrate, you average out with respect to alpha. And then the connection with nu is completely explicit. This is the same thing. This nu k is a distribution, a probability distribution in the space of matrices. Those are the matrices that you have the right to use. So you take the pre-image of the domain D by all of your matrices, you take the average with respect to the choice of the matrix, and that should be equal to the measure of D itself. Okay? So we have that the exponent can be characterized in that way as a maximum. So, and phi, let me remind you that phi is the function that to each x and v associates the logarithm of ax of v over v, the expansion function. Okay, so take any eta k stationary for nu k that realizes the maximum such that lambda plus of nu k is the integral of that function phi with respect to mu k times eta k. Take any stationary measure for nu k that realizes the maximum. Okay. Again, if you want to make this integral more explicit in terms of eta k, what you have is logarithm. I'm replacing the expression of phi. Logarithm. Now, a of x only depends on the zeroth coordinates. This is just a matrix. So alpha applied to v divided by v. And then you integrate with respect to eta, to nu k of alpha and eta k of v. I mean, this involves the whole sequence x, but since it only depends on the zeroth coordinate, you immediately get this. Okay. So for each k, we have one stationary measure that, one or more, but we pick one that realizes the maximum. Now we're going to try to go to the limit. So the sequence eta k is a sequence of probability measures on the projective space. And the projective space is a compact metric space. So the space of all probability measures on the projective space is compact for the weak star topology. Okay? So up to taking a subsequence, up to restricting to a subsequence, we may suppose that eta k converges to some eta in the weak star topology. Okay. I guess it's clear what I'm trying to get at. I want to get lambda plus of nu. So I want to use a similar formula for lambda plus of nu. And this seems like a clever thing to do. Now, first of all, eta is stationary for nu. That's okay, because of a proposition that I stated last time, which said exactly this. The space of stationary measures is closed even when you give yourself the right to change the base measure, and you can. Okay? So this is fine. But this doesn't prove what I want yet, because lambda plus of nu is the maximum of this. Oh yeah, there's a second observation, which is that the integral lambda plus of nu k, so it's equal to the integral of phi d mu k times eta k, which is equal to the integral of log alpha of v over v d eta k of alpha d nu k of alpha d eta k of v. This converges to the integral of phi d nu times eta because eta k converges to eta in weak star topology. And nu k converges to, which this is just the integral of the same function with respect to nu alpha and the eta of v, because it's just the definition of weak star topology. This function here is a continuous function in the domain. The domain here is alpha in GLD and V in projective space. This is a continuous function. We even have this stronger fact that this convergence is in GD. So if this measure converges to this and this measure converges to this, the integral converges. Okay. we should be slightly careful here because the function is continuous, but it's not bounded. This function is not bounded in general. Alpha varies in the group of all matrices. So the matrix could be very big. And if it's very big, then this number is very big, which means that the function is not bounded from above. But that's not a problem because anyway, all these measures, nu and nu k, have compact supports. Nu has compact supports in the group of matrices. So there are no big matrices in the support of nu. And the support of nu k is contained in the neighborhood of the support of nu, and so it's also compact. Okay, this is one of the places where it's useful that that the support of nu is compact, first of all. Secondly, the support of nu k is contained in the neighborhood of the support of nu, and so the support of nu k is also compact. Well, I can write it like this. It's contained in the closed ball around the support of nu, and this is compact. And so this function, the function log of alpha v divided by v is continuous and bounded. And when we define the weak star topology, we say that if we have a continuous bounded function, then the integrals with respect to the sequence converge to the integrals with respect to the limit measure, and that's the definition of weak star topology. Okay. Very often we deal with compact sets, compact spaces, where continuous functions are automatically bounded. If they are not, we have to be careful to make them bounded. And in this case, that's not difficult because the way the topology was defined. These are nu and nu k's are in the space of matrices, but they don't contain matrices that are very big. Okay? So this is just because of this convergence. Okay, so what can happen then? What do we conclude? So we conclude that the limit lambda plus of nu k is there, is just the integral of phi d nu d mu times eta, or if you prefer, log of alpha v over v d nu of alpha d eta of v. Okay? And I would love to say, I would really love to say that this is equal to lambda plus of nu. That's what I want, right? But there's a little problem, which is that lambda plus of nu is the maximum of those integrals taken over all stationary measures. Okay? And eta is one stationary measure for nu. So what I am able to extract from this argument is that the limit lambda plus nu k is less or equal than lambda plus of nu, which is not fantastic because I already told you that lambda plus is an upper semi-continuous function. So we are rediscovering that. This formula also proves that the lambda plus is an upper semi-continuous function. Here's the proof. It says that it is equal if the cocycle defined by nu is completely irreducible. Everything that I'm writing here is not interesting. It's not going to help us in the proof, but I want to, if I go too fast, you will get the impression that the proof was over here. It's not, it was just beginning. But this is not going to help for the proof. Why? That's Furstenberg's formula. Furstenberg's formula that we proved last time says that if the cocycle is completely reducible, then all stationary measures realize lambda plus. Okay? And it also says, another uninteresting observation, is that that we have equality if, by any chance, if it happens that your measure, your stationary measure, does realize, maybe we are lucky, and it does realize the exponents. Okay? I mean, so what I want to say is that if we were lucky and we by chance found a stationary measure that realizes the exponent for nu, then we are done. So in what follows, we are going to assume the two things that I wrote before, that lambda minus of nu is smaller than lambda plus of nu. That's the first thing. And the second thing is that we were unlucky and the integral of phi d mu times eta is strictly smaller than lambda plus nu. Okay, so I'm not going to repeat this all the time. These are standing assumptions from now on. Of course, that means, by Furstenberg's formula, that the cocycle is not completely reducible. Okay? But I'm going to say something stronger than that. And that's this proposition here. By the way, this here was observed by Furstenberg and Kiefer 30 years ago. And they call this the continuity theorem. If you have a cocycle which is completely reducible, then it is a continuity point for the exponents. Okay? Furstenberg, Kiefer, I think it's 1983. But they also said that probably if it's not completely reducible, it's not going to be continuous. That's where they were not right. Okay, so proposition under these assumptions, there exists so far the dimension was not very important. Now I'm going to one of the places where I'm going to suppose that the dimension is 2. There exists some line in projective space satisfying So a of x applied to L is equal to L for mu almost every x. So there's a line which is invariant under almost all matrices. This can be rewritten in terms of nu. Just a reformulation. Alpha of L equals L for nu almost every alpha in JLD. So this already proves that the cocycle is not even irreducible. I mean, completely irreducible, you don't want to have any finite family of subspaces that is invariant. So there exists some finite family, but I prove here, I state here that there is one subspace that is fixed by all the matrices. That's even stronger. The other condition is that the limit 1 over n log a n x v is, so this is the Lyapunov exponent, is strictly smaller than lambda plus for every v in L minus 0. So this line is not only invariant, it is a line where vectors necessarily grow slowly. And the growth is equal to lambda plus of nu if V is not in L. Observe that this line does not depend on x, okay? This is really one line, not a function, not a bundle. No. It's a line. So, so you have R2, and you have some line L, such that if you have a vector in this line, V, then by almost all matrices, the vector remains in L, and it grows slowly. And all the other vectors that are outside, of course, they remain outside, and they grow much faster, at a rate of growth that is strictly bigger. Oh, yeah. And there's a third fact, which is you look at the stationary measure that we found in this construction, and we look at the weight of the set formed by this line. So you see, we are in projective space. We are looking in projective space. L is a point in projective space. I look at the set formed by this point. It has positive measure. So the measure eta is necessarily atomic on this point. Okay? So we have all these three properties. And I'm going to prove this, and then next time we will explore this. I mean, if we knew that the cocycle is completely reducible, then the game would be over. We would have a contradiction here. But we will develop consequences of this proposition to prove that such an L cannot exist. Not for a stationary measure eta that was obtained in this way. Eta is a measure, stationary measure, that is obtained as limit of stationary measures for nearby probability distributions. We will not prove that this cannot exist. We will not prove that this cannot exist for any stationary measure. But we will prove that if your stationary measure for nu was obtained as the limit of stationary measures for nu case, then this eta doesn't have the right to have an atom like this. Okay, and that's how the theorem comes out. Yeah. Yeah.
So in fact, this continuity theorem holds even.
Yeah, it holds. This is always the case. It seems silly in the middle of the proof to say, if something I don't know was true, then I would be done. The reason I wrote it is that I'm going to prove that this happens, and the proof actually ends here. But we will have to work 2 more lectures or so to realize that it ends here. This is necessarily true. If I assume it's not true, then I get a contradiction. Okay? So the nice thing about proofs by contradiction is that once you're done, everything you did so far is useless. Okay? Everything I'm going to say, very clever ideas and so on, are about the empty sets in the end. But we have to do it to know that it's about the empty set. Okay, so how do we get this proposition? Okay. Yeah. So proof of the proposition. It starts with something that we are already quite familiar with. We're going to consider the Birkhoff average, time average of phi. Which we know is equal to the limit of 1 over n log of an xv. Okay. So we know that the integral of phi twiddle d mu times eta is equal to the integral of phi d mu times eta by the ergodic theorem. We did this 3 or 4 times by now. And we are assuming that this is strictly smaller than lambda plus. Okay, so this function, this is the Lyapunov exponent in the direction of v. This is always less or equal than lambda plus. And our assumption means that the integral is less or equal than lambda plus, is strictly less than lambda plus. Okay? So the conclusion is, well, couldn't make it, that that phi twiddle of xv is smaller than lambda plus for a set of pairs xv with positive mu times eta measure. cannot be equal to cannot be equal everywhere, almost everywhere, because the integral I don't even need this observation, because okay, for a certain set of pairs with positive measure. Now, this set is PF invariant because the function is PF invariant. This is still the ergodic theorem. Time averages are constant on orbits, so the set of points where this function is below lambda plus has to be an invariant set. Okay, here is the first claim. So I'm going to look at this set, the set of x, v, such that phi twiddle of x, v, is strictly smaller than lambda plus of nu. Why am I looking at this set? Because I believe in the statement and the statement tells me that this set is formed by the pairs x, L. Okay? The statement tells me that this set should look, according to the statement, this should look like this. Here is M, here is projective space, here is the line L that I want to find. If the statement is correct, then this set consists of this. Right? The only vectors that grow slower than lambda plus are the vectors that are in L. Okay, so this is what I want to prove. Let's call this L. So here's the first claim. I'm going to move in that direction of proving that L looks like this. So here's the first claim. For mu almost every x in M, there exists exactly one point Lx in projective space such that phi of x Lx is less than lambda plus of nu. So what I'm saying here is not yet that, is something like this. For each point x, I have exactly one element of projective space, PR2, where the growth is smaller than lambda plus. Then the next step will be, so I'm saying that this set script L is a graph. And then I will have to prove that the function is continuous, is constant. Okay? Uniqueness. So I'm proving this claim. There's one more statement. Moreover, if I take L of x and I apply A of x to it, I get L of f of x for mu almost every x in M. So this bundle is invariant. So uniqueness is very easy. Just have to think. Suppose you had two. So you have a point x, and this is projective space. And suppose you had two such directions. You have L1 and you have L2, such that the limit, so phi twiddle is written here, such that the limit 1 over n log of anx v1 is smaller than lambda plus, and the same is true for the other direction. For v1 in L1, different from 0, v2 in L2 minus 0. Suppose we had two of these directions. I think it's clear what I'm going to say. Given any vector, v, arbitrary, I can write it as a sum of a v1 and a v2. Okay, a v2, v1. The iterates of v1 grow slowly. The iterates of v2 also grow slowly. So this would imply that the limit 1 over n log anx v is smaller than lambda plus of mu for every v in R2 minus 0. But lambda plus is the largest Lyapunov exponent. Is equal to lambda 1. So some vector has to grow at lambda plus. So this would contradict Oscillators. When we proved Oscillators, we proved that lambda plus is the rate, by definition, is the rate of growth of the norm, but it's also the largest Lyapunov exponent. So some vector has to grow at this speed. Yes? So Maurice is asking whether this is not LX is V2 in the second subspace in the Oscillators flag. Yes, it is. I mean, this says that it is. But I want to find it, and I want to find it in a way that invariance would come out from that, but I also want to prove this. So I'm reconstructing it in a sense. Okay? Also, I'm stating this proposition for dimension 2. There's an extension for higher dimensions. The main difference is that L is not necessarily one-dimensional. Could be one-dimensional, even in higher dimensions, but may not be. But yes, this is V2. But there's a magic thing. This is Vx2. There are two magic things. One is that it does not depend on x. Okay, this is what's fantastic about this. In general, this is a function of x. It can vary a lot. It will not depend on x, and it is an atom for the stationary measure, which is also not true in general. I mean, it doesn't really make sense when V2 depends on x. Okay, so in a sense I'm reconstructing the Vx2, and yes, you're right. This uniqueness, if I think of oscillators, I mean, it has to be unique. If Vx2 had two dimensions, then it would be equal to Vx1. That's essentially what I'm saying. Okay, so this is uniqueness. Now, existence. Existence. Let's look at the set of points x in M such that phi twiddle x v is smaller than lambda plus of nu for some v in projective space. So in terms of this picture, I'm looking at those points x such that there exists some vector here, some direction that does grow slower. Okay. Well, this set, I don't know what to call it, n has positive measure. Measure for mu. Why is that? Because of what was written here and I erased. Because phi twiddle d mu times eta is less than lambda plus implies that phi twiddle of xv is less than lambda plus on some positive measure set. Set of pairs xv. So there has to be a set of x's with positive measure, which can be coupled with some v, and we get this. Okay. The measure here is mu times eta. If the set of allowed x's had zero measure for mu, then this would not be true. Okay. So this set n has positive measure for mu, and the other property is that it is invariant. Under F. And that's because this set is invariant, right? It's because of this. This is PF invariant. If you have a point and a vector that grows slowly at this point, you take the image by PF and you go to f of x, ax of v, okay? And this point here, this new point, has the same Lyapunov exponent, the same phi twiddle as this one, because this function is invariant. Phi twiddle is constant on orbits. So if this vector grows slowly when you start iterating from x, then this vector grows slowly when you start iterating from f of x. The function, the dynamical, the most important dynamical system here is PF in the product, the skew product. Okay. The function phi twiddle is constant on orbits. So if it is strictly smaller than lambda plus nu here, then it is still strictly smaller than lambda plus nu there, which means that over a point f of x, there is some vector that grows slowly, and so f of x belongs in N. Right? Now, the f is a Bernoulli shift. So if you have an invariant set with positive measure, Bernoulli shifts are ergodic. So you conclude that N has full measure. Which is precisely what I said, existence. For almost all points, there exists some vector where the growth is slow. Okay. For mu almost every x, there exists exactly one direction where the growth is slower than lambda plus. So I proved uniqueness, I proved existence, and now I have to prove invariance. This is demonstration by staring at the picture. Just look at the picture, and what does the picture say? If for a point x you found this direction where the growth is slow, and you want to know which direction corresponds to f of x, I just told you, it's the image. Stare at the picture. When you apply the cocycle, cocycle does f of x here, and here does a. That's what I said. If you take the direction that grows slowly at the point x and you apply the matrix, then you get the direction that grows slowly at f of x. There's nothing more to be said. So as Mauricio pointed out, so far we didn't do anything very spectacular. We just rediscovered Vx2. But now, now comes something a little bit more more fantastic, which is that there exists L in R2 such that such that L of x is equal to L for mu almost all x. Okay. So let me prove this claim, claim 2. So I had this set, right, L. I had this set L, set of such that phi twiddle x v is less than lambda plus, which at this point I may write as the graph of L of x, because I already know that there's exactly one direction here, and eta of L, sorry, not eta. What is the measure? The measure is mu times eta. Mu times eta of L is positive. Okay, that's what is written here. The set of pairs where phi twiddle is less than lambda plus has positive measure for mu times eta. Yeah. Now, there's more than one way to proceed. In the book, I chose to be lazy and do it the quickest way, but there are other ways to argue. Remember that every stationary measure can be disintegrated into ergodic measures. So take eta 0 to be an ergodic component of eta. This I didn't detail that very much in class, but this also means that mu times eta 0 is an ergodic component of mu times eta, perhaps in a more familiar sense, because here I'm talking of invariant measures for the projective cocycle. But not any ergodic component. Mu times eta of L is positive. So I can always find an ergodic component which gives positive weight to this. So such that mu times eta 0 of L is positive. Okay? So what I'm doing here, just for fixed ideas, what I'm doing here is the following. Eta may be written as a linear combination of stationary ergodic measures as a convex combination. This means that mu times eta is just a restatement, is a linear combination, convex combination of measures of this type, which are invariant and ergodic for the projective cocycle. Okay, and this means in particular, this means that mu times eta of the set L is integral of mu times eta alpha of L d alpha. Now this is positive, so the function has to be positive somewhere. This here, and I just take any of them. Any of these eta alphas in the ergodic decomposition that give positive weight to L. Okay. I can leave an exercise, not an easy exercise, but accessible. Prove claim 2 without using ergodic decomposition. That can be done. You have to be a little bit more intelligent than I was, but it can be done. Okay, so I take an ergodic component that gives positive weight to this. Now, the set L is invariant. So, mu times eta 0 of L is 1 by ergodicity. L is an invariant set. We have used that a few times already. Right? So we have this situation. We have a graph. To each x, we associate L of x. We have a product measure, mu times eta 0. And this measure, this product measure, is completely supported on the graph. What this means is that if you use Fubini, this says that 1 is the integral of mu times eta 0 applied to L, which is the integral of of eta 0 of Lx integrated with respect to x. I'm just using Fubini here. For each x, I integrate with respect to eta 0. Since this is a graph, there's only one point to look at. And then I take the integral with respect to mu. Okay? So how can it be true that the integral is 1, given that this is always less or equal than 1? Well, the only possibility is that this is always equal to 1. Okay, so this implies eta 0 of Lx is equal to 1 for mu almost every x. So this measure, this probability measure, is completely located. It's a Dirac mass on Lx for all x. Now, Dirac masses are very well resolved measures. They are in a point and that's it. So this also implies that Lx is constant on a full mu measure set. If there were two values of Lx, eta 0 would have to be Dirac mass on one and to be Dirac mass on the other. But that is not a Dirac measure. Okay? it gives full weight to Lx independently of which x that is. So there can only be one value of Lx. And so that's what I claim here. So immediately, as a consequence, look at this. I already knew that this graph was invariant. So this formula here tells me this. Okay, which was part A of proposition. This is just this formula once I know that L of x does not depend on x. Okay. Part B is immediate by construction. This region that I'm drawing all the time consists of the unique direction where growth is slower than lambda plus. In a sense, I cooked up the demonstration so that the proof so that I would get this. Okay? There was a part C, which was that L is an atom for eta. Well, mu times eta of L is bigger than 0, right? That's what is written here. But now that we know that the function is constant, now that we know that the picture is like this, we can use Fubini again. And Fubini tells me that this is mu of m times eta of L, right? This is a product set, and I have a product measure. And this is eta of L. So eta of L is positive, and that's precisely what I wrote it here, and then I erased. Okay. So we are going to stop here. Of course, these two standing assumptions imply that there exists a certain subspace, a line, that is invariant, in a sense, a contracting direction, and an atom. I'm going to say that this line is invariant because of this property, and I'm going to say that it is expanding because of this property. At this point doesn't make much sense because I just said that it's a contracting line, but I'm going to argue that it's an expanding point. And what I will prove is that any invariant expanding point cannot be an atom for any measure that comes from perturbations of the cocycle. That's how we will get the contradiction. Okay? Okay, that will be next Monday.